direction fields and Euler's method. Okay. What do these things possibly mean? Okay. So, as we discussed, most differential equations cannot be solved cannot be solved easily. So therefore, in a lot of cases, we need to use approximations or use methods to get an idea of what our curves will look like, what the solution curve looks like. And these two things are two ways to do that. Okay, so we'll break this up into two parts. Right, the first part we're going to talk about direction fields. So what is the direction field? Well, I'll demonstrate by giving an example. So let's say that we're given the equation y prime equals x plus y. Okay. Now, this is, I could potentially solve this using a method we're going to learn in 9.5, but for the moment, I don't know how to solve this thing. And so the question is there a way that I can at least look at what y is doing in each case, or maybe get an idea of the curve? And absolutely we can. So let's think about this, right? So this is y prime equals something, right? So this is a derivative, right? What this says is that if I want the derivative at a particular point, I just take the x coordinate and the y coordinate of that point and I add them together, right? So if I'm looking at point 1, 1, for example, y prime at 1, 1 is going to be just 1 plus 1, just 2, right? Or if I have the point 3, 7, then y prime is going to be 3 plus 7, which is 10, right? So at each particular point, I can actually see what the derivative looks like. And using that, I can create a picture that kind of where I'm going to put all these different slopes on my picture to see how everything moves, how everything kind of moves together, right? So we'll just kind of take this plot. We're going to put points onto it, right? So let's think about 0, 0 first, okay? If I have 0 plus 0, then I just get 0, right? So y prime is 0 at that point, but that doesn't really tell us, right? And that doesn't say if I'm moving up or down, it just kind of means I'm stable. So in a way, this is just kind of a null point. Okay. Now 1, 1 we did, right? So maybe I'll go ahead and plot that point. 1, 1. We have a slope of 2, right? So what I'm going to do is I'm going to model that on this picture. I'm going to say, okay, if at 1, 1 I have a slope of 2, then I'm going to draw a little line that represents that. So we're going to have 1. It doesn't have to be perfect, but doesn't let you kind of get the general idea. I'm going to draw that. Okay, so I just drew a little segment of a line that has a slope of 2. That looks like it has a slope of 2, right? So that's going to be approximately, that's what the slope is at that particular point. Okay, and I'm going to continue to do this, right? So if I do 1, 0, that's 1 plus 0, that's 1, right? So I have a slope of 1. If I do 0, 1, I get the same slope. If I do, now if we go into the negative numbers, it's going to get a little interesting. If I do negative 1, 1, that's 0. So nothing's happening at that point, right? It's kind of a flat. Maybe you could draw it. That would be, no, you could maybe draw a flat line in that case. Right, because we have a horizontal tangent line at that point. Okay, so I have a flat line. If I do, so we'll just keep putting points on here. Negative 1, 0, we're going to get negative 1, so we're going to have a slope that looks like this. Same thing down here. My slope is going to look like that because it's negative 0, negative 1. We can keep doing points. I'll do negative 1, negative 1, which is going to be negative 2, so it should be steeper going the other way. Here is 1, negative 1, so that's also flat. So we could actually like kind of get a, as we keep testing points, what we're going to see is everything along that diagonal is going to cancel out. So we're just going to have horizontal tangents at each of those points. Here we're going to, on the axes, our slope is just going to keep getting steeper and steeper. in one way or the other, like that. Wait, let me. Okay. And we'll do the same here. So we're steeper, steeper, steeper. Steeper. And then let's see. So here we have two -1. So it'll look like this. So we also, this diagonal here is going to have slope 1. This one should have slope 2, etc. Right? And I'm going to keep filling this in until I get enough points and I can say, okay, this is what the slope is doing at each of these different areas, right? So again, maybe I'll just kind of finish out what we have going here so far. Okay. Right, well, we're going to get something like this. Right now, if I want to understand what the solution curves of this thing looks like, right? Let's just take one in this area, right? What's going to happen, it looks like, is that I'm going to have a solution that is going to travel, right? If I look at the points this direction, it looks like as I move along the curve, it's kind of moving down. And there might be some, in specific cases, that might maybe pick up in some way, right? So I might have a solution that's going to curve up, right? Similarly, I might have something, looks like I have some sort of equilibrium here, or this could cut off earlier and cut it up like that, right? And I could have another solution curve that's going down, down. Again, there's some points that we could, let's see. This one actually looks like just keep it down, but you're kind of maybe seeing the image of what's happening here, right? I'm taking these few points that I have, plotting them and saying, okay, well, this is probably, so I can see if I go down this way and my points kind of curve around, I'm going to get this slope, right? The picture draws, I think, again, if I did some a little higher, here, it has one go sooner, maybe something like this. But we can see that with our sketches, with the different lines, right? And so these things, this picture that I drew is what we call the direction field, or you can call it slope field. It has various names, but we can use these to just study the different points and then do it as a cohesive whole to say, okay, this is what some solutions look like, right? And you may get problems at certain points, right? That give you a particular, so like a initial value, right? You get in, like, it may want you to pass through, in this case, maybe 0, 0, right? And so you want to draw the solution that's going to pass through that point. So you kind of look before that point, look after that point, and see where your lines are going. And you want to follow that path. You say, okay, I want to follow that. Yes.
The slope is that value in relation to what? You said it was the slope at that point.
Yes.
But is it the slope in relation to the point before it or after?
No, it's just the slope at that particular point, right? Remember how I found them? I find the slope by just plugging in the point. That slope doesn't have anything to do with the point before it or after. I just plug that in. Now, when I connect the line, then you're going to kind of see them flow into each other, but there's nothing about the point 0, 1 that's going to tell me anything about the slope at 1, 1, unless I know the graph, of course.
So it's not describing an explicit function.
What?
It's not describing an explicit function.
Well, we don't know, right? That's why we're doing this graph to kind of see what's going to happen. If we knew what the function was, we could probably say a lot more about it. But this is really the most we can do at this point, right? We have some that are going to pick up steam fast and go climb, right? There's going to be other ones that have to go down a little while before they pick up. But there might be some that never get a chance to pick up. They just get stuck in a certain spot. And there's going to be some, like if I took this thing and said equal to 0, there's going to be some spots that are just what are called equilibrium solutions, like numbers that if I plug it in for y here, it's just gonna won't give me. So. Okay, does this kind of make sense? again, so I give one doing the homework. There's a couple of examples in the book, but at the same time, probably don't need to do a whole bunch of these. We can't, if you want me to, I'll do another one. Does anybody want to see another one? You're just gonna take a few points, right? Generally, I think the graph that I give, I just have it go to like, I think I have like 5 at most. I probably was nicer though, just like kind of go in those directions. I think I gave the one I gave also was like something like this, which seems hard, but really isn't going to be too bad. Yes.
So when it once you draw one specific solution that passes through the point, are you just drawing with many there, or is it really just making one?
There's gonna be one that looks like it fits the most.
Okay.
Right.
It'll
Now,
make sense like when you see it.
yes. Now, ultimately, like in reality, there's gonna be like, you know, we did at like these easy points, right? But there's also gonna be slopes at the more complicated point, you know, like talking about 0.05 and point, you know, something like that. So technically around the point, there's gonna be an infinite amount of them, but the initial value you're gonna be given is going to be something simple like that. And so based on the lines that you drew, there should be a clear winner in that case. Okay, so yeah, if it asks you to draw one at a particular point, again, just, I think maybe I put X here or something, but you plot, you know, whatever the function is, you plot the different slopes, right, onto the picture. And if it gives you one specific solution to do, right, so on this one, again, if it was like, you know, plot solution at 0, 0 at the origin, right? Then you would want to draw this one. You'd say, okay, this is where it hits the origin, right? And it looks like beforehand, this is kind of the path that it takes. And then afterwards, this is the path that's going to come out. Okay? If you don't get it perfect, that's okay. Not meant to be perfect, of course, because they're only can be a general picture of it, but this is what we use. And you can imagine computer programs do this a lot better than humans can, because they can do it a lot faster and do it in more detail. Okay. Cool. Any questions on this? Okay. That's really all it's asking for. So if I'll read like, let's see. It's like some of the problems are going to be like sketch the direction field of the differential equation, right? So you're going to be given. Let's see, I'll just write like numbers 10s, for example. So you might be given the equation y prime equals x minus y plus 1. Okay, so you're going to take the time and you're going to plot a graph, and you're going to say, okay, at 0, 0, if I put 0, 0 in there, I get 0 minus 0 plus 1. So my slope is going to be 1 at that point, right? And you're going to do that for whatever other points you can kind of fit in there, right? And then that you'll have your whole picture, right? Which is going to come out in some form. It looks like this. It's going to look a little different. And then it might say sketch a solution curve that passes through. Not all of them do, but some might ask that. And so when it gets to that point, if it says the one that passes through 0, 0, you know, you might have slopes that are going like this, right? Around, and then maybe it does something like this, the slopes do. And so you're like, oh, okay, well, I want the one that goes through 0, 0, so it looks like it's going to do something like that, right? It comes into it and comes out of it. That's what we get. Okay, so that's all you'll be asked for. Okay, so nothing too bad. Nothing really to write much, just more visual. Okay, any questions for that before we hop on to Euler's method here? It's pronounced Euler, by the way, not Euler. Some of you who took, some of you might know that because you use Euler's identity there. But, okay, good. Let me erase this problem. Okay. Let's start with Euler's method. So, if you don't want to do this, that's okay. Maybe you're not as interested in the solution curve, but maybe you want to use the differential equation to estimate just the function value at a later point, which you can absolutely do. And that's what Euler's method is for. So let's take the curve. Right? Imagine it's something, you know, like this. Let's say that I have some differential equation, which the book is going to notate this in the form of, let's see, they say f. Okay, so if I have a differential equation, which is equal to some function of t and y, so I have some t and some, like I have t variable and I have y variable. I don't necessarily have to have both, but there's going to be at least, you know, it can consist of those variables, right? If I have this differential equation, and this is what the actual solution curve looks like, right? Although I don't know, I may not obviously know what it is. What I can do is if I know an initial condition, right? So if I know like y of 0 is 1, for example. So I'm given this and I'm given this guy. Okay. I may not know what the solution curve looks like, right? And I'm just drawing it here so you get like a pictorial of what we're doing. But what I can do is I can say, okay, I know what the slope is at that point though. So maybe I can use a tangent line to my advantage, right? You remember you've used something, you know, you would use, you could use a tangent line to a graph to kind of approximate values nearby to it. And so we're going to do the exact same thing here. Now, obviously, if I want to get this point up here, approximate this point, then the tangent line to this point here is not going to do very well in approximating this point because there's still going to be a little bit off. Okay. But what I say is that, okay, this part of the curve is pretty close here. So maybe what I'll do next is I'm going to go over a little distance, right? Saying maybe this is still close enough to the curve in some way. And I'm going to find another tangent line. So I'm going to build off of this point on the line and create another line. Okay, so I say, okay, I did this first approximation of using the tangent line, and I'm going to say, okay, this one is pretty close to the curve. So now let me assume that's on the curve, and I'm going to make another tangent line to that point. And so notice, oh, we're getting a bit closer, right? And this only gets better as you add in more points, right? So maybe I'll use green here. But if I did, okay, here's a point, and then I went to this point, to this point, to this point, to this point, right? I use these different lines to approximate along the way, right? That's going to get us pretty close to what the solution is, right? And there is an easy process to do this, which we call Euler's method, okay? Now, how this works is I'm going to, in order to find, right, because each time I'm going to find a different y value, okay? So I'm going to be given a step size, okay? Step size, and it's going to be, we'll call it h in this case, but this is sort of our delta x, okay? So this is how far between the x values I'm going, okay? In order to find the next y value, the next y number on my graph, right? Maybe I'll write the first one. Let's say I'm given y of x0 equals y0. So I'm given some initial point. Then, in order to get y1, I'm going to take y0 plus h times f of, and in this case I wrote t, but it can be x as well, the function as exponent x0, y0. Okay, now let's think about what that is, right? Hopefully this might look a little familiar to an equation we've worked with before, right? Point slope form, which says that y minus y naught equals m times x minus x naught, right? Where in this case, the y naught has just kind of been added over, okay? But in this case, m, right, that's my slope. That is this f of x naught, y naught, right? Because that's what the derivative is, right? And that's normally where we should put the value of our derivative. And then x minus x naught is going to be our delta x, right? That's the difference between the two x's. Okay, so that's why we have the h here. So in each case, I'm saying, okay, to get to the next one, I'm going to use the linear approximation to get to this next guy, right? Use having an individual step size along the way. So from here, right, to get y2, I'm going to get y1 plus h, right, because we just found my one, of f of x1, y. Now, to find x1 is just going to be x0 plus h, right? Because if I start at x0, then I just add the step size to it, the delta x, to get to the next x, right? So that is my x1, right? And then if I wanted y3, it would be the same formula, except instead of all the ones, I'd have all the twos over here, et cetera, et cetera. So in general, we're going to have yn equals yn minus 1 plus h times f of xn minus 1, yn minus 1. Where I'll just say x I right now, is going to be xo plus I. Okay, so again, you can remember it that way, or you can just say, okay, to get to the next x, I add the step size. So if I start at x equals 1, then the next x is going to be, if the step size is, let's say, h.1, then the next x is going to be 1.1. Add another 0.1, it's going to be 1.2. Add another 0.1, it's going to be 1.3, right? That's going to be each of your x's, x1, x2, x3, x4. But this is what there's not, okay? And so we can use this to approximate the solutions to, or approximate points on my solution curve for my differential equation. Okay, so to demonstrate this, and again, maybe they also have this written down. Maybe it's easier to remember it that way. This is just saying from XO in general. This says if I know xi minus 1, I just add h to it, and that gives me that. Okay. Good. So let's do an example. Any questions so far on this? Okay. Hopefully the structure makes sense. We're just using a bunch of lines, right? Just as always. We're either using rectangles or lines. That's where really all that boils down to, right? So yes. Actually not. No, this is not a good term to an integral. So nope. We still use lines, but in this case we don't do an infinite amount and then add it up. Now I think they may take the principle of this and then apply it in some way, but Euler's method itself doesn't get used for any sort of integration. So let's go and do an example. I'll just take this cursor again. So let's see if we'll pick just a problem here. Let's see. Okay. We're going to do number 22 in the book, which says to use Euler's method with step size 0.2 to estimate y of 1. where y of x is the solution of the initial value problem. We're going to talk about that. Y prime equals x squared y minus 1/2 y squared, and y of 0 equals 1. Okay. So here's all of our information, right? We're going to use Euler's method to estimate y of 1. So we know the differential equation, and we know what y of 0 is, and so we're just going to take as many steps necessary to get to y of 1 in this case. Okay. So let's go ahead and kind of label everything that I have right now. So we have, let's see. Do I know what h is in this problem? What is it? 0.2. Good. Right. That's our step size. So h is going to be 0.2. What is x0 going to be? Right. What's our first x we start with? Not 1. We're going to get to y of 1, right? Well, 0. Y of 0 is 1. So we're using x0 0. So what's y0? Why not? 1. Yep. Good. So x naught is 0, right? Because again, this is where the x goes here. This is x and this is the y value. Okay. So we have x naught is 0, y naught is 1. And so that almost gives us everything we need to start off Euler's method. But we also need to establish what is f of x, y in our case? What is that function? Anybody? What is it? Yeah, it's just what y prime is. Absolutely. F of x, y is going to be x squared y minus 1/2 y squared. I erased it already, but remember I had this. Okay, so that f of x, y is whatever the derivative is. Okay, you could technically like write that and say like, oh, that's where y prime goes, but it's easier to maybe think about it in this form. So that's my f of x, y. Okay, so my step size is 0.2, and I start off at x is 0, and I want to get to x is 1. So how many steps do I need to take to get there? 5 of them. Good. Because we need to do 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.2, which is going to be 1 altogether. Okay, so let's just do the first step. So step 1, y1 is going to be yo. I'll go and write down the formula first. H f of xo. Okay, so we're going to get 1 plus 0.2 f of 0. Okay, so what is f of 0, 1 going to be? This page, right? So x is 0 and y is 1. What do we get? Negative 1/2. Fantastic. That term disappears and we just get negative 1/2. So we're going to get 1 plus 0.2 times negative 1/2, which I could just write as 1 minus 0.1. Because the 2 just cancel away. And what's 1 minus 0.1? 0.9. Okay. So that is my approximation, at least for the y value at. What is it? So you're absolutely right. That's the point. It's the same thing as 0.5, right? But I'm saying I want half of 0.2, which is the same thing as, I could write 0.2 as 1/5, as 1/5 as well, right? So if I take 1/2 of 1/5, I get 1/10, which is 0.1. Yeah, which you could also write this as 2/10. So half of 2/10 is 1/10. So that was kind of my logic there, but yeah, may not always be the same thing to do. But yeah, that's why I was like, that kind of is kind of. Okay, good. So we get 0.9, right? So that's my y1. Does that make sense so far? Good with that, maybe. Good, awesome. Okay, let's just finish this one out, and then we'll be done with the lessons today. So, okay. So I'll just start. So y2 is going to be, again, I'll write down this one, y1 plus h f of x1, y1. Okay, what is y1 again? What's y1? 0.9, we just found that. Plus 0.2 f of, what's x1? X1 now, right? So x0 is 0. So now we need to go to the next x, right? So we take x, we can take x0 and add the step size, right? We just add it once. So what's 0 plus 0.2? It's 0.2. 0.2, and we put 0.9 here. Okay, so you're going to notice the math isn't going to be the easiest thing at this point, so I'll probably pull out a handy calculator to get us through here. So we're going to have 0.9 plus 0.2. So I take 0.2 and 0.9 and plug it into my function, which is going to be, so x squared y. And if anybody wants to calculate this with me as well, just to confirm my answers. F, so we want to do 0.2 and 0.9, which is going to give us about negative 0.369 in that case. And then we calculate it, so we get 0.9 plus 0.2 times negative 0.3 with 0.826. Okay, so again, just calculator work, making sure you get down to your answer, but we get about 0.862. Make sense still? We good? Okay, so again, we continue on. I'm going to do y3 equals what? So what is this one going to look like in this case?
0.2 plus.
Good. So again, y2 is just going to be 0.8262. H is still 0.2. Okay, now what is x2 going to be in this case? Zero 0.4. Awesome. 0.4, and then we're going to put 0.862 in. Okay, which is going to leave us with, so it's kind of fast, we get 0.826. So this is going to be approximately, so I do have to do approximate out, 0.7884. Okay, there we go, 0.7844. Y4, what's this one going to look like? Yeah. So again, we just plug in, so 0.7844. It's okay if it's approximate, it's all approximation anyway, so maybe not, just make sure you're plugging in the right number still though. 0.2, what's x3 going to be? So x2 was 0.4. What is it? 0.6. 0.784. So then we take that and plug it in. Let's see. Y3 plus 0.2 f of 0.6.3. And this is going to be 0.7793 approximately. Okay, and then last but not least, y5. So this is the one we wanted, right? Because this is going to be the y at 1. Okay, so we get, what's the equation here? Fantastic. So we're going to get that 0.7793 plus 0.2 f. What's x for? 0.8. You just add the step each time. 0.8 and then times 0.7793. So let's see, I'll call this y4. So then we're going to get y4 plus 0.2 f of 0.8. What? So we end up getting 0.818. So y1 is going to be approximately 0.8183. Okay, so that's the best guess we have at the moment, using all those methods that we can get. Again, there's always a possibility we could solve the equations we're given, but we can't really do that as of now. So this is what we have. Any questions on this at all? Okay, do you feel like you can do this? It's just plugging in. Hopefully I've hammered it enough now that you just, to get x, you just keep adding the step size. But then you just keep plugging in the y's at every step. And that's going to be it. Okay? Okay. Good. Yes. It will be doable numbers. Yes. I will never get something on a test that's just really gross things. Like the numbers should be nice, right? And that should be helpful because if you're taking the test and you get really bad numbers, probably did something wrong. Like on the partial fractions one, sometimes they solve fractions there. I wouldn't give fractions for those. Those would always be whole numbers. So you can always go back and check that if you do that. Okay. Great. Well, I'm going to go ahead. Is there any last questions on this? Yes.
How did you know that you're going to stop at like 5?
So remember, we said x is 0 is 0, and I wanted to get to y of 1. So I want to get to x is 1, right? So if the step size is 0.2, how many times do I need to add the step size to get 5 times? So that's why we go to y5. You could also like kind of calculate the x at each time if you were keeping track, and then but you'd see x5 is 1, so you're like, oh wait, I'm done. Okay, good. If that's good there, I'm gonna stop the recording. We have like a lot of time left. I won't keep you here if you don't want to be here, but I am more than happy to take any questions.